I am Dr. Ohenia Gold, and this is Science on the Street. We're going to jump right into our main topic for today, plastic, that nature and life-saving material that has lived long enough to see itself become the villain. How did this fossil fuel byproduct go from hero substance to mortal enemy, and how does so much of it end up in the ocean? Now, as a good millennial, I listened to Captain Planet and learned to RECYCLE recycle from that one episode of Rocker's Modern Life. But even Gen Xers have their own environmental PSAs. Gen Z has grown up in this literal dumpster fire, so buckle up because this one is personal. In the 1950s, many household items were being made out of natural materials like cotton, tortoiseshell, ivory, and glass. So insatiable was the demand for these materials that people started to notice the populations of hawksbill turtles and elephants diminishing. An alternative had to be found. Companies started pouring money into liquid polymers, byproducts from the fossil fuel industry, to try to make suitable replacements. Celluloid was the first successful plastic polymer made from the cellulose, part of the cell wall, of cotton. Even though it exploded on contact when turned into billiard balls, it was a fine replacement for tortoiseshell combs. Expensive-looking, cheaply made combs became all the rage and started the path towards today's world of disposable conveniences. As other plastics developed, new uses were continuously found. The IV bag, for example, made from PVC mixed with di-2-ethyl-hexyl phthalate, also known as DEHP, provided a flexible, unbreakable bag that preserved red blood cells and allowed oxygen to disperse. This was a clear advantage over the rubber tubing and glass bottles that blood used to be stored in, which were breakable, let in bacteria, and damaged the blood. The same PVC DEHP mix is used in medical tubing like that in dialysis machines and in the tubing used to care for neonatal infants. However, the workers making the plastic mix were developing health problems, and it was soon found that DEHP was leaching out of the plastic and into people's blood and staying there. So next time you get an IV, you can sit next to Regina as an official member of the plastics. On Fridays, we wear BPA. In today's world, many consumer goods have some portion of plastic in them. Our foods come wrapped in plastic, even the produce, to extend its shelf life. It's nearly impossible, or at least extremely difficult, to live a plastic-free life. But it's okay because of the recycling program. All of those plastic single-use products get returned to the manufacturers to be given a new life as a different plastic item. Soda bottles can become carpets, fabrics, or maybe even a new bottle. All those little numbers in the chasing arrow triangle at the bottom of plastics mean they can be and are recycled, right? Well, as it turns out, not exactly. The numbers inside the symbol were intended to let manufacturers know what kind of plastic something is made from. The different numbers cannot be recycled together. The number 1 plastic is PET, which is highly recyclable and can be washed and remade. The other numbers, mostly, used to get shipped to China and other Eastern Asian countries for processing, where they get sorted by hand, by color and type, like some dystopian The Home edit, turned into plastic pellets and remade into something else. And that's only if you live near a coast where shipping containers are likely to arrive. If you live somewhere inland, it is more likely that those same higher number plastics that you are dutifully sorting each week are ending up in a landfill. Our Americans are recycling more than ever, but not enough to outweigh our consumption of plastic. And the problem doesn't go away once in the landfill. Natural materials decompose and their elements are returned to the ground to be taken in by other organisms. Plastics do not decompose. They merely break apart into smaller and smaller plastics. They migrate away from landfills, or from overfilled trash cans on street corners, or from your own recycle bins on windy days, wash into rivers, and eventually into the ocean, where literally hundreds of species accidentally consume them or get entangled and die. Some of them even use it as an accidental fashion statement. The use of plastics saved endangered animals in the short term, only to cause them death by 1,000 tiny microplastics decades later. So much has washed into the ocean that there is now an area twice the size of Texas that is teeming with more plastic than wildlife. Can you imagine oceanographer Charles Moore when he came across that area? Ah, a new pristine land untouched by humans. Oh wait, it's more garbage. And that's not even the whole story, because we couldn't even cover how responsibility for plastic disposal shifted from producers to consumers, and how many plastics contain endocrine disruptors that leach out from the plastic and mess with our hormone levels. So from their humble beginnings as combs to their modern life sailing the high seas, what can be done to curtail this problem? Organizations like the Ocean Cleanup and others have designed specialized equipment to skim the floating garbage off the top few meters of ocean without reeling in wildlife. They've deployed river cleanup water wheels like Mr. Trash Wheel in Baltimore's Inner Harbor to stop the flow of plastics into the ocean. Research teams are investigating ways to turn plastic back into fuel, bacteria that can eat the plastic and turn it into other plastics, and working up actually biodegradable plastics. An important step we can take is to reduce our consumption of plastics, especially the single-use kind, close the loop by reusing those we do purchase, and support legislation that moves us away from plastic ubiquity and aids in the cleanup. Without better policies in place, the future could be looking mighty grim. To find out more about plastic's many facets, we spoke with two guests. First up, we have Dr. Kelsey Stocker, physical chemist at Suffolk University. Welcome, Kelsey. Thank you so much for being here.
Hi, thanks for having me.
Can you tell us what even is plastic?
So plastic is an example of a polymer. So it is a chain made up of tiny identical units called monomers. And when you string together thousands of those into a line that are all bonded together, you make a polymer. And so at its very core, a plastic is just many, many of these polymer chains all together making a bulk material.
Is that what gives plastic its flexibility and how we can use it to make so many different kinds of things?
So there's actually a second kind of secret ingredient that you need to make most polymers useful.
The secret spice.
Secrets, right? I bring the goods. So the polymer chains are the real major building blocks of a plastic, but usually need additives, typically a plasticizer, to give it the properties that we love about plastic. So without a plasticizer, a plastic would be more rigid and brittle and maybe even a little bit chalky, so a lot less useful to work with. You can also add additives that do things like make it a different color, maybe make it UV resistive, right? All kinds of interesting things, but you really want a plasticizer in there to make it more flexible and more interesting.
Interesting. So plastic itself is not just this string of molecules. It has to have this other component in order to make it functional for all of the things we use plastic for.
Yes. And there's a huge menu to choose from. You can really customize them.
What happens when that infinitely customizable menu breaks down?
Yes. That plasticizer is the answer again. So if you think about these really long polymer chains, we're not, in a chemical sense, terribly worried about them breaking down. They're really strong bonds, they're very stable. What we do worry about is that plasticizer leaking out, because these are not actual size, but much, much smaller units. They're maybe the size of one or two of the monomer units that make up your whole polymer chain. So if you think about these really long polymer chains all kind of existing together, and then in between those chains, you would have your little plasticizers. So they're there making sure those chains don't get too entangled with each other. And that's where you get that flexibility again. The unfortunate thing is that the plasticizer isn't as strongly bound to those polymer chains as the polymer chains are to each other. So a really great example that I actually lived through in college that we all did was this plasticizer bisphenol A, or BPA, that you see everywhere now. So I started college in 2004. I dutifully bought my first Nalgene.
I did too.
Took it everywhere with me.
Yep.
And by 2007 or 2008, it was everybody get rid of your Nalgenes. They're making them now without BPA. You can still see it on canned food, right? So BPA was also a really common additive to the epoxy that lines pretty much all canned food.
So canned food is not just a steel can or a tin can. It's or aluminum, not tin, but
yeah, they're all lined with an epoxy resin.
Cool.
Yeah, so people were able to demonstrate that even through normal washing of a Nalgene bottle or a generic plastic bottle, that BPA was able to slip out from between those polymer chains and end up in the water you were storing it in.
Does the same thing happen with canned food? Do we have BPA just swimming around our cans of peas and carrots or whatever?
Not anymore.
Oh. Excellent news. Bringing to you only the best news here at Science on the Street. So along with that, so we know plastic, when it breaks down, it leaks out these plasticizer bits. How does recycling play into this? What role did recycling, was it supposed to have that's not quite working?
So recycling of plastic is really interesting for a lot of reasons. So when plastic does get recycled, I'll start with the positive, it undergoes what we typically call mechanical recycling. So it literally does just get washed, sorted, ground up or shredded, and then maybe re-melted into pellets or flakes. And then it's resold or given back to a manufacturer, and they can use it to make new plastic goods. The trouble with recycling plastic is that you don't get the same quality of plastic that you get from starting with a fresh resin or petrochemicals. So it typically, or if you recycle a drink bottle, that is never going to be used to make another product that would hold food. It might be made to hold fibers. They sell fleece jackets now that say made with water bottles.
I have a pair of shoes made from water bottles.
Yes, yeah. So
very comfortable.
It does get another life, but that's actually called downcycling. So it's used to make a different type of product. Then the loop never quite closes. Unlike glass or aluminum, which are really kind of infinitely recyclable, the quality doesn't degrade, and so you could just keep making glass bottles out of glass bottles. And with plastic, it's kind of a waterfall, where you start with the highest quality that the FDA lets us use to contact food, and then it gets used to make clothing, and then maybe that would get used to make something for landscaping, and then eventually it can't be recycled anymore.
So does each plastic, if we have a number one, like a PET plastic, does that actually go through each number on its life cycle, or does some of it just end up in landfill after its use?
Oh, it's a good question. It would always remain the same type of plastic, so it would retain its number, but it would be used to make a different product.
I see.
Typically, if it's recycled at all.
I have heard that you are planning a course on plastics. Can you tell me a little bit more about that?
I am. So this is going to be a first-year seminar here at Suffolk that I'm offering for the first time this fall. There's currently one section that's designated for CAS honor students. And I'm really excited about it. I think it's going to be fun. I thought I was being sneaky, getting a little bit of polymer science into the first year curriculum. But I'm going to take students into the lab a little bit. We're going to make a bioplastic. And I think it's one of the most pressing issues of our time, and I think we're all thinking about it a lot more. So I'm really excited about it.
So you mentioned bioplastics. Mm-hmm. How is it different from a regular run-of-the-mill plastic?
Very good question, because there's actually a lot of misconception about what a bioplastic is. At its most generous, it means a plastic that's been made with some kind of alternative to conventional petroleum or fossil fuels. That doesn't necessarily correlate to it being biodegradable or more recyclable or any better on the other end. It just means that it was maybe made with more renewable energy.
Yeah, so you're not relying on the fossil fuel industry to create the plastic.
Exactly.
But it might not be returned to the environment the way something natural would.
Right.
Gotcha. How does that break down? You have mentioned that it's not quite as biodegradable as the word bioplastic might make it seem. Mm-hmm. What's the breakdown process on a bioplastic?
It would depend a lot on the plastic. So even with non-bioplastics, they're all their own special little creatures. And so we have something like PET that you mentioned that's incredibly recyclable if it makes it to the recycling plant. We also have something conventional plastic like PVC that I have heard called the Satan's resin.
I have heard that as well.
It is, a lot of the qualities that make it fabulous, that it's durable and fairly inert, also make it really difficult to deal with and recycle. Another issue that we need to think about when plastics break down is, of course, this leaching of plasticizer. That's kind of the paramount chemical concern. There's this other mechanical concern that it can physically break down just into smaller and smaller pieces. And so now we're hearing a lot more about microplastics and even nanoplastics. And the effects of those we're still just learning about. And even at that level, we can think about there being kind of a chemical effect and a physical effect. So the chemical concern or effect of a microplastic is we don't really understand yet how long they spend in our bodies and how well they accumulate or where they accumulate. So the concern there would be that it's allowing, just due to the small size, this plastic can access and stick around in areas of our body that big plastic can't. So it could potentially just be ramping up our exposure to these plasticizers that would continue to leach out of the plastic waste. The physical concern when something is that small is that it can just cause issues as a foreign body, right? So if you inhale it, that can cause inflammation or issues in your lungs. Depending on where else it sticks around, it can promote allergic or inflammatory responses. So there's a lot of angles to plastic at every scale.
When we end up talking about all of these microplastics and microplastic fibers and things that end up in the ocean, and animals like fish and invertebrates are consuming them either accidentally or because they confuse them for natural prey. We then go and fish up these organisms and eat them ourselves. So is that contributing to the accumulation of plastic in us, or are we able to process the plastic inside of our food differently than plastics that like we're drinking out of bottles or whatever?
That's a very good question, and we don't totally know. So we're still working on estimates as to how much microplastics an average person might consume in a year. So I've heard an estimate of about a credit card's worth, which still feels like too much.
Thank you for all of that information on plastic chemistry. Thank you for being here.
Great, thanks for having me.
To understand how plastics affect wildlife, we zoomed with Dr. Nadine Lysiak, whale biologist at Suffolk University. Welcome, Nadine. Thank you so much for being here today.
Thanks for having me.
So you're a whale biologist. Can you tell me a little bit about that?
Yeah, I study baleen whales, which are the large species like humpback and right whales and bowhead whales. And I look at their ecology and physiology. So what habitats they use, where they migrate to, reproductive patterns, and also stress physiology.
How do you examine stress in a whale? Like, do you go out, because I imagine you can't go out on a boat and just follow a whale around.
Well, some people do. You can measure hormones, stress hormones, in a number of different tissues. So people who follow whales out on boats might collect feces or skin and blubber and collect hormones from those tissues. But I actually study baleen, which is the filter feeding apparatus inside of the mouths of large whales. And we have to get that from dead animals. So when a large whale dies, a dissection or a necropsy is performed. And people who are in charge of coordinating that will collect baleen plates for me.
How does ocean plastic affect whales?
So ocean plastics can affect whales in two different ways. They can ingest it, or they can become entangled in it. So in terms of ingesting, there are really small particles of plastics like microplastics that they can ingest, and we don't really know how those impact the animals in terms of their health and toxicity and things like that. But some whales will accidentally ingest large objects, and those can get trapped in their digestive system. They can't break them down because they're plastic. That can cause injuries, or it can actually plug up their digestive system. And then in terms of entanglement, that can happen in plastic debris or fishing gear that's actively being utilized, or gear that's been abandoned, which is called ghost gear. In any of those cases, plastic debris or line or netting can become wrapped around whales. And in the case of smaller species, they often drown in these kinds of debris pieces. But for larger whales, they're strong enough to sort of break out of some of these, especially for fishing gear, break out of these configurations and swim away with gear tangled around their bodies. And that's a problem because it can constrict their ability to swim, can cause injuries, it can impact feeding. and it probably impacts their survival and reproductive success. And then in some animals, it can actually be fatal.
So I imagine, I know if I were to be entangled by large amounts of garbage, that I would feel quite stressed out. How does that sort of stress show up in your research?
We can imagine that if our body was wrapped up in line or rope, it would probably be very stressful. It might actually also be painful and cause a lot of distress in our lives. So for whales, I actually take baleen, which is a very long keratin tissue. So it's made of similar proteins as things like human hair and nails. And I sample the baleen plate at regular intervals. In each of these samples, I am extracting and measuring the concentration of hormones called glucocorticoids. These are secreted as part of the vertebrate mammalian stress response. So anytime an animal is impacted by a stressor, their bodies will set off a cascade that ends in these hormones being secreted, and it's a survival mechanism to try to help them, escape a threat, or things like that. So for animals that are entangled in fishing gear, we think that they're chronically stressed. So in the baleen, we should see high levels of glucocorticoids that persist over long periods of time.
What other sorts of life events can influence stress hormones in whales?
That's a great question. So through our research, we're actually finding that there are many internal stressors or natural stressors that also induce a stress response. And one of those is actually pregnancy. So we found that in times when we know animals are pregnant, by measuring other hormones like progesterone, we can see that things like cortisol, corticosterone, stress hormones are actually elevated. So, it's important to understand that there are very normal and important natural stressors that also impact the physiology of whales.
I can vouch for pregnancy being stressful on behalf of all mothers.
Yes, I think most humans can vouch that it is a stressful process.
How can understanding these hormones help us piece together the life events of whales when we can't really observe them 24/7? And how can it help us address things like plastic pollution in the future?
Yeah, that's a great question. So the first part of your question, that's why baleen is such a cool tissue to study in terms of hormone analysis, because we're generating these continuous but retrospective, or sort of back in the past from when the whale died, back several years into its life, to really reconstruct what happened to it. How many times did it give birth? Where did it migrate to? What stressors did it experience? So it's helping us understand basically a continuous record of what was going on with this animal. So in terms of management, what we can do with that, in one sense, it's giving us a really quantitative picture of how entanglements physiologically impact large whales. So this helps us understand, how significant these events are. I told you that some animals actually die from gear entanglements, but many others are able to shed or get out of them and continue swimming, on their way in the ocean. But that entanglement event, can really dramatically impact them. We think that there are significant sublethal impacts to an entanglement that might impede an individual's ability to grow, its health, and its ability to reproduce in the future. So some of the species that I work on are very endangered, highly endangered. And so that's a big issue, knowing that there's sublethal effects of entanglement that can impact their ability to grow as a population. And it's also a little bit of evidence that fishing gear entanglement, plastic debris interactions are an animal welfare issue, that these animals can experience chronic stress response and really have a tough time interacting with some of the plastic and other debris that we have put into the ocean.
When you mention entanglement in these fishing gears, that includes both fishing gear that is being actively used and that's just been abandoned in the ocean? I always had this
Correct.
picture that, fishing gear, once it wasn't being used, it would get collected somehow and disposed of somewhere. But is that not the reality?
Yeah, so there's a very big problem with what's called ghost gear. So ghost gear is fishing gear that has been abandoned, or more often it's gear that's gotten lost. So maybe a fisherman has set the gear, and it's drifted away because of storm events or things like that, or currents have pulled it or dragged it or moved it. So it's not always something that's intentional, but it's gear that's not actively being fished anymore. And that can cause, basically present risk for whales to become entangled in it. There's many kind of environmentally minded or conservation nonprofits that run ghost gear removal trips to try to minimize the impact of this. But there's a lot of ghost gear in the ocean that impacts not just whales, but all kinds of marine species like sea turtles, seabirds, fishes, etc.
What would you say is the most important thing we can do to help address this problem?
On the individual level, people can minimize their plastic consumption. So this includes being mindful of what we're buying and what we're disposing of. In terms of fishing gear, there's lots of work being done that includes scientists, fishermen, the government or federal managers to try to modify gear so that it doesn't pose such a risk to whales. So this can include gear that sort of sits on the bottom without lines or nets up in the water column, modifying where and when we fish to try to be mindful of whale migration patterns and habitat use. And then the last one is sort of the biggest scale, is like corporate responsibility. Try to put in congressmen and people in government who can help make laws and oversight to try to minimize plastic pollution, plastic packaging, and all those kinds of things that make it into our oceans.
Thank you for being with us today, Nadine. This has been Science on the Street.